Okay, we're back. Welcome back, everybody. So here's what we were talking about last time. We were talking about the cross product. It's defined by this weird formula right here. But we've noticed that there are a couple of algebraic conveniences. So for one thing, weird though this formula is, it is equivalent to this symbolic determinant, which is very easy to remember. And again, this is the only formula I've ever memorized for the cross product. I simply don't trust myself to get the order right. I'm quite sure I would switch some minus signs somewhere along in there. But the determinant formula I've already memorized, and so no problem. Okay, so I strongly encourage that. And then we also noticed that we can construct this thing called a triple product. And that even though this isn't directly about the cross product itself, this construction involves a cross product, right? And it is also an easily remembered formula. Another way to think about this, by the way, is this is an alternative point of view on what a determinant is. Right? You can think of a determinant as being, well, it's this thing in systems of equations and the volumes of parallelepipeds or whatever, but you can also think of determinant as being just straight up a triple product. Right? Okay. So certain facts that we observed, the cross product is always orthogonal to both of the input vectors. Again, let me just remind you, we're not going to go through the proofs in this section. Makes me sad, but we just don't have the time. So, if you want to see these very cool, very geometrically satisfying proofs, they're right here. Take a look. I'd be very happy to talk about them in office hours if you have any questions or if you want to hear it said or whatever the case may be. But we just don't have the class time for it. And where we ended last time was this kind of cycling identity here, that if you have a triple product and if you kind of cycle through, the C, you put it where the B was, and the B, you put it where the A was, and the A, you put it where the C had been, right? If you just kind of cycle through, that doesn't change the value of the triple product, which is super weird, right? But different ways that you can see it. Of course, you can just directly brute force, plug and chug compute, or you can make some clever arguments about how triple products relate to determinants and determinants relate to volumes and order, and this is a much cooler argument here. Again, we don't have time for it. Sad. Okay, all right, so that's where we left off. So, next fact that I'm sad we don't have time to discuss the reasons for. The magnitude of the cross product by itself gives you the area of the parallelogram defined by the two vectors. So in particular, you got your first vector A, you got your second vector B. Those two vectors, between the two of them, define this parallelogram. Right? And the area of that parallelogram is equal to the magnitude of the cross product of those two vectors. It's very surprising, yes.
Is there a reason why the notation only has the magnitude lines on one side?
Yes, because this is not a reference to a magnitude. This is a little notation that I may have made up myself. I'm not sure. If I've seen it before, I don't remember where. But this is my little shorthand for a parallelogram. So the idea is these two parallel lines represent parallel, which is itself very standard, but then following it by a list of two vectors, I mean the parallel thing that's defined by those things. And then elsewhere I refer to a parallelepiped with A, comma, B, comma, C. Yeah, right. Is that cool? Is everybody happy with the notation? Okay. All right, so again, super neat fact, very clever proof here. Give it a look if you're curious. We don't have time. You're not responsible for it, but it is pretty neato, and it's a nice exercise in thinking about all these different tools that we're developing about cross product and determinant and blah blah blah. So if you're looking for an exercise, if you're looking for a little mathematical weightlifting to see if you can test your understanding of these ideas, follow through this proof. Okay, yeah.
Can we use this cross product for like vectors with 4 dimensions, or is it max?
So the cross product as what I'm going to call a binary operation is peculiar to 3 dimensions. So again, as a binary operation, namely when there's just 2 things that go in and 1 thing that comes out, this is what we call a binary operation. Only 3 dimensions. Now, of course, in the exercises, you may recall you saw a generalized cross product. It's not a binary operation. It's if you give n minus 1 vectors in, and you want 1 vector out that has analogous properties. So you can call it a product. It's very different. Yeah. Does that make sense? You happy?
Yeah.
Okay. All right. You can ask me after class if you have other questions. Feel free. Yeah. Okay. All right. Okay, next one. Cross product being the 0 vector means that the pair of vectors is linearly dependent. Now, this actually may kind of ring a bell in a way. You recall that if the dot product is 0, then the vectors are, I'm going to loosely say perpendicular. They're either perpendicular or there's a 0 issue, right? So, but basically perpendicular. Of course, we have a word for this. The word is orthogonal, right? But I want to keep it geometric. Roughly speaking, exceptions granted, dot product equals 0 means perpendicular. Well, cross product equals 0 pretty much means parallel. Because again, 2 vectors being dependent, other than zeros issues, right? Dependent means the 2 vectors are parallel. So it's kind of complementary in a way to the dot product. Cross product is a great way to see if 2 vectors are parallel. You could argue, and dot product is how you tell if they're perpendicular. Okay. Again, cool proof. Don't have time. Exercise. All that. Okay. Now, I'm going to deliberately misstate this next theorem just because in practice, how you're going to use it most of the time. The deliberate misstatement is that this list is in right-hand order. Now, that's, of course, a misstatement. Technically, A could be the 0 vector, in which case, there is no right-hand or left-hand order. Right? It just doesn't work. So the cleaning up of this statement is that it's never in left-hand order, which basically, again, what this is saying is that this list is either right-hand order or we have 0 problems. Right? So loosely speaking, we think of it as being right-hand order. So easy argument. Again, we don't have time for the proof, but take a look. If you're looking for an exercise, I have a related exercise here. If you look at this list of 3 vectors, and you ask what is the dimension of the span of those 3 vectors, we've got 3 vectors. The dimension of the span's got to be 3 or less. What's weird is that it's never 2. It could be 0, it could be 1, it could be 3. Can't be 2. So again, if you're looking for a little warm-up, practice problem, the argument involves both linear algebra that you've seen before and also new facts about cross product and stuff. Okay, no, I'm not going to have myself. One of the last things I'm going to say about cross product, I think we're on the last page, is notice that when we defined cross product, we wrote it down as a formula. It was an algebraic definition. And then I promised you there to be good, cool geometric facts coming, and of course we've seen quite a few of those already. The book, again, takes a different approach to all this than I do. The book starts with this purely geometric description of the cross product. They don't write down the algebra at all. They say, let's define the cross product to be the unique vector that has these properties we've already talked about. Purely geometric. They're talking about perpendicular, they're talking about area, they're talking about handedness. All geometry, right? And based on this purely geometric description, they then it's a different argument, of course, but they effectively work backwards and come up with the formula. They derive the formula as a result. And the reasons I don't do that are, for one thing, it's harder. And if you don't believe me, look at the book and look at all the nasty algebra they have to do in there. I think it's quite a bit harder to do it that way. The other reason is if you define the cross product as this, it leaves you asking, why would I define this thing, right? In other words, to me, for my intuition, it's not, oh, well, yeah, intuitively satisfying. Of course I should have a name for this thing because look how natural that is. It really doesn't seem that way to me, right? It looks like a kind of a weird thing, something whose magnitude is the area and right-hand order, and I don't know, it's just not clear why this is something I'd want to talk about. So, to me, the advantages are low and the disadvantages are high. Again, it's just an opinion, but be aware that is how the book approaches this. Okay. We're going to view this as just kind of a nice summary of quick facts about what we know about the cross product. Okay. Alrighty. Another little fact that, by the way, follows from these. If you take these three facts, you can derive this one, that if you switch the two vectors in a cross product, you don't get the same thing. In fact, though, you get exactly the negative of the same thing. So kind of a neat fact. And again, it immediately follows from this. And again, we don't have time for these proofs, so this is another exercise to think through for yourself. But one of the big takeaways of this theorem is simply that cross product is not commutative. You can't just kind of switch the order around like you can in most other products, right? If you're multiplying numbers, switch the order around. Doing dot product of vectors, sure, just kind of switch them. No problem. Not the cross product. And of course, as you saw in Math 218, also not matrix products. Right, so just something you got to keep in mind. We get accustomed in high school to a certain kind of feel of how we do algebra, right? And we do algebra by you write these things, and you're allowed to kind of move factors around in a term, and you're allowed to move terms to the other side of the equation with a minus. We just kind of get used to certain things, and you have to remind yourself that when you're talking about a cross product, you got to unused to yourself this commutativity sort of thing, because it does not work for cross product. You have to put in a minus sign if you switch the order. Alrighty. So one more fact I want to put in, I guess two more. Anyway, some more stuff not in the book, and to me, this seems like a missed opportunity. Really cool fact about the cross product: it's linear. And again, now this is something that y'all did the algebra of previously, but I want to flesh that all out here. If you think of cross product with a fixed vector A as being a function, which it is, right? You give me an x, I give you an output per this formula. That function is linear. And again, what does linear mean? Linear means that if you do a linear combination inside, you get effectively the same as doing the linear combination outside. Or said differently, if you do the linear combination before you plug into the function or after you plug into the function, same thing. Okay. All right. And what I've stated here, let me do it like that. So this version has the fixed vector on the left, right? The cross product is with a vector on the left. It also works if you do the cross product on the right. Also linear, just like that one is. Okay. So, neat and very fundamental fact, and I think it's worth mentioning. Okay. And then lastly, and I think this really is the last fact, is this is another heads up. Cross product's not associative either. And it's not even close. It's not like it's off by a minus sign. It's just, they're just not equal. Right? So another thing to be careful of, again, we get accustomed to certain conveniences doing algebra, and it's easy to play a little fast and loose with it based on that experience. Doesn't work. It's going to get you into big trouble. Okay. Alrighty. A couple of quick applications. Not going to spend a lot of time on these. This is just in case you're curious. Why do we need the cross product? What is it good for? In terms of physics and stuff. And we're going to get some really, really powerful answers to that, by the way, later in the course when we're doing divergence and curl and this kind of stuff. There's some powerful, deep answers to that question. Right now, immediately accessible, couple observations. Torque is computed by a cross product. Right? Torque is a cross product of your sort of radius vector, if you will, and your force vector. So that's just there it is, right? That's a very natural physical quantity. By the way, if you haven't seen torque before, it's not that deep of an idea. You know how force means how hard you're pushing on something? Torque just means how hard are you twisting on something. It's like I like to call it an angular analog of force. It's like force, but, around instead of forward. Okay. All right. Cross product. Another immediately accessible one, if you have a charged particle that's moving with some velocity, and it's moving through a magnetic field like this, an observed fact of the universe. And by the way, don't ask me why. It's not about that's not what we do in science, right? We don't know why things work. We talk about how they work, what can we quantify, but why did the universe get made this way? No idea. Right? But the observation is that the velocity times the charge cross the magnetic field that it's moving through will tell you the amount of force that's going to subsequently be applied to that charged particle. And again, this is just empirical. Weird though it is, charged particles moving in a magnetic field causes a force to be created. And again, cross product. Okay. Everybody with me? All right. Okay, so that is 1.4. We move along now to section 1.5. Some of this you may have seen before. Again, all of chapter 1, I think all of the sections of chapter 1 in maybe bits and pieces, some bigger bits, smaller bits, who knows. Some of all of this is probably covered in Math 218. But anyway, I'm going to talk about most of section 1.5 here because I'm just not sure what y'all have seen. And it's good to review it anyway. Okay, so let's talk about the equation for a plane. How do we write down the equation for a plane? And which plane, you ask? I've got to tell you what the plane is before we can write down the equation for it. Now I'm going to describe the plane by way of two things. A vector in that is perpendicular to the plane. Importantly, perpendicular, not orthogonal. I can't use the zero vector. It's no good. I need it to be non-zero, right? And then a point that's in the plane. Okay. All right, so that's the plane I'm talking about. And given that information about the plane, how would I find the equation of the plane? So I'm going to start by writing down a test. It's a geometric test, not an algebraic test, but nevertheless, I'm going to write down a test and then I'm going to rephrase it. And so one test that I could make, again, given that my plane contains the point x naught and is perpendicular to the vector in, I can look at this difference vector, x minus x naught, as relates to, this vector x that I'm trying to decide, this is the vector I'm trying to decide, is that in the plane or not in the plane? And so the observation goes like this. If, as I have here, if the point x is in the plane, now I appeal to the picture, if x is in the plane, we were given that x naught is in the plane. I got 2 points in the plane. When I subtract them, that difference would need to be parallel to the plane. So this that difference vector is parallel to the plane. So that's a test. Now it's geometric and not particularly, immediately useful because we don't have an immediate test for how to, is a vector parallel to a plane, right? But being parallel to the plane, I argue means that it's also perpendicular to the normal vector. And if it's perpendicular to the normal vector, then then the dot product is 0 here. And that's an algebraic test, right? So starting off with a geometric argument, we translate it into an algebraic argument. How we doing? Everybody's happy? Okay. All right. By the way, this goes both ways. Let's entertain the idea of a point that is not in the plane. I'm going to look at a point up here, x, and then here's my x minus x naught. Right? And if the point is not in the plane, as per my drawing here, then again I argue, and this is a geometric argument, but the point x is not in the plane. Well, x naught is in the plane. When I do that subtraction, it can't be parallel to the plane, which means it can't be perpendicular to the normal vector, which means that it can't be that this dot product is 0. So it works both ways, right? In or not in the plane, this is a test to decide which way it is. Okay. So with all of that established, I'm going to rewrite things just a little bit now. First observation, that you can take our equation here and distribute the dot product and move things around a little bit. No big deal. A little bit of vector algebra. You can rewrite it as this. This is the more standard way to write it, even though it's a little harder to relate to the geometry, but it's a little easier to write on the page. Doesn't really matter. And then I can take my normal vector. Again, that's one of the givens. Let's say it has coordinates A, B, C. And I can dot with the point that I'm testing, x, with coordinates X, Y, Z. Right? That's how a dot product works. And then don't forget, n and x naught are both given. So I don't need to leave this in that form. I know both n and x naught. I can just crank out that dot product, and it is some value that I can just write. It's some number, known. So let's call it D. And so then here's our rewrite then, alternate version of the equation of a plane. Looks like this. And it's pretty satisfying. It looks a lot like the equation of a line in 2 dimensions, doesn't it? It's just kind of one extra term, if you will. So pretty satisfying. Yeah.
So if we had like a plane and then a point somewhere, could we find out like the perpendicular from that point to the plane?
Oh yeah. So that's a harder problem. That's going to be later on in this lecture. Yeah, but we'll get there. Yep. Actually, we might not get there today, but we'll. Anyways, very soon. Yeah. All right. But just to be clear, though, just in case. If you have some point that's not in the plane, right, you don't need to have it's not like the normal vector for this point is somehow different from the normal vector for that point. That's not in some sense what we're interested in. Okay. All right. So here's something kind of cool, though. If what you start with is the equation of the plane, there's free information encoded in this equation. Specifically, don't forget where these numbers came from. These numbers A, B, C, where they came from, they're the coefficients of the normal vector. Right? So neat fact, right? If you see an equation for a plane at a glance, you can instantly determine what that normal vector is, or one of the normal vectors for that plane. So that's something to keep in mind. Very useful. Okay. All right. So here's an example. Suppose I have 3 points, A, B, C. Here they are. A, B, C. And suppose I want to find the equation of the plane that contains those 3 points. How would I find that equation? Okay, let's go back up here. Here's what we know about the equation of a plane. The equation of a plane looks like this. That's how you do, write the equation of a plane. And what do I need in order to be able to write this down? I mean, I would love to just write that down. There it is. Well, apparently, though, in order to write this down, I need to know what n is. Right? And I'm also going to need to know x naught, and keep in mind what x naught's job is. X naught's job is just to be a point that's in the plane. Okay, so I need a vector perpendicular to the plane and a point in the plane. How am I going to find that from what I actually know about this example? Let's start with an easy one. Where am I going to find a point in this plane? Oh, hey, good news. I have a bunch of them given to me. Just because I'm lazy and I like zeros and small numbers, I'm going to pick that one. Doesn't have to be the first one. Pick any point you want in the plane. It doesn't matter. I'm going to arbitrarily pick the easiest one. So I'm going to use that as my x naught. Let x naught be A. Everybody on board? Now the harder part, how am I going to find the normal vector? The normal vector is certainly not given. Normal vector, I need a vector perpendicular to the plane. Perpendicular to the plane. How am I going to find a vector perpendicular to the plane? I can't immediately do so, but what I can immediately do is I can find some vectors that are parallel to the plane, right? Subtraction of points that are in the plane gives me vectors that are perpendicular. And let me do it like this. Two vectors that are perpendicular to the parallel to the plane. Is everybody on board? Okay. By the way, if I misspeak at any point, shoot that hand right up and help me out. It's verbal stumble sometimes happens. Okay, so now let's remind ourselves, I've got 3 points in the plane. Can't use that immediately to find a normal vector. Now I have also 2 vectors parallel to the plane. Does having 2 vectors parallel to the plane help me find a normal vector? Why, yes, it does. I can take these parallel vectors and I can take their cross product. The cross product will be perpendicular to the plane. Does that make sense to everybody? Kind of a geometric appeal there. Yeah.
Could you also do the reverse order?
Oh, yeah, sure. You can, yeah, that's right. So, great question, and let me talk a little bit about normal vectors. I'm going to go back up, actually, to up here. So, this normal vector here is a vector that's perpendicular to the plane. So yeah, it is perpendicular to the plane, but so is this one, and so is that one. And there's actually a bunch of vectors that could serve as the normal vector, right? And it doesn't ultimately make any real difference in the resulting equation, but any vector perpendicular to the plane is fine. So now what's going to happen if you, as you asked, if you were to switch the order, if you were to do C minus A cross B minus A instead, all that would happen is you're switching the order, and that would just make the normal vector point downward instead of upward. No problem. All good. Everybody's happy? Great question. Thank you. Okay. All right. So one thing I want to talk about on this example, this is an example of what I like to call a math puzzle, right? I give you certain things, and then I give you a goal, right? I have this. I want this, and you've got to kind of figure out how to use the tools that you have to start with what you're given and cleverly work your way up to what you need, right? And 2 seconds. So there's a bazillion versions of this where you have certain geometric givens or possibly even algebraic givens, and then you've got to get to some desired end. And the puzzle is just to figure out how do I connect the dots. And in this case, the idea was subtractions followed by a cross product. That's what gets me from what I have to what I want. It'll be different with every such puzzle. Yes.
What do we call A, B, and C? Vectors or points?
Here I'm viewing them as being points, but again, this is a distinction that we blur. The role that they're serving here is to define locations, and locations, you view them as points in order to use them as a way to describe locations. But it always remains that I could, if the origin, for example, were, let's say the origin were here, it's always the case that even though this B, for example, I'm thinking of it as a point, I could think of it as a vector if that were somehow relevant. Now, it isn't in this case. The how far B is away from the origin, or what direction is B from the origin, totally irrelevant here. All right, so here I want to view them as points.
Or as vectors, you mean, in this case?
No, B I want to view as a point. I don't want to view it as a vector because I don't care about this. I don't really care about where we are relative to the origin here, right? So B I need to view as a point. But notice that this difference I need to view as being a vector because I need to know about the direction. I don't care about, in this case, I don't care about where that point is. This point is irrelevant. Does that make sense?
Yeah, so just in terms of notation, because you put A vector.
Yes, I use the same notation for both because the context always makes it clear, right? So, and that's the point. So the reader has to be kind of heads up on this as to, okay, wait, what is this thing doing? What am I interested in about this thing? And therefore, which way should I interpret it? And the B here, being as it is a point that is in the plane, in means we're talking about location. Location means I'm viewing this as a point. Yeah. Okay. Is that cool?
Yeah.
Yeah. So it's a constant heads up situation of interpret appropriate to the context. Yeah. Okay. All right. Okay, moving along. Here's a neat fact. This gets used in various circumstances. And there's another version of this that we'll talk about later. If you have an equation for a plane, and if mysteriously there's no y's in it, right? The y term just isn't there. Well, that's a little eyebrow raiser, right? I mean, how strange. There's an equation involving x, y, and z, except there's no y's present. What does that mean? Geometrically, what does that look like? Is the question that I want to entertain. I claim the answer is that plane is parallel to the y-axis. If there's no y's in the equation for a plane, that plane is parallel to the y-axis. Now, this one, I'm going to show you the argument. There's not that much to it. It's pretty straightforward. Again, no y's. It looks like this. That means that this coefficient is 0. That means that altogether the three coefficients are A, 0, and C. Right? It's A, B, C, but B is 0. And if that's the case, well, this vector, easily checked, is perpendicular to this vector. Keep in mind that vector defining the direction of the y-axis is 0, 1, 0. Right? Easy to check that these are perpendicular. Right? And then I make the intuitive appeal if the plane is perpendicular to that normal vector, and if the normal vector is perpendicular to this y-axis, geometric appeal, then the plane's parallel to the y-axis. Everybody buy it? Okay. So, easy argument. But a good fact to remember, and if nothing else, I mean, it's something to sort of just keep an eye out for. Sometimes you will find that you've got an equation for a plane that only involves two terms on the one side. And then you can immediately remember, you don't have to go through this argument again. You can say, there's no y's, therefore it's parallel to the y-axis. Okay. All right. Okay. Here's just another example. And again, this section has got this subject, this topic within the course. There's a lot of sort of like puzzles of you have this, you want this, how do you get there from here? Kind of questions. Okay, so here we've got we've got a plane. We've got another plane given. We've got some point given. That's all given. And what I want to find is I want to find a parameterization of the resulting line, the line in particular that's parallel to both of the planes and that contains the given point. All right, so we got some givens. We have a goal, namely the parameterization of the line. How do we get there from here? And again, it's a puzzle. As you know, we've got to think about how to put the pieces together. Okay, so big idea. First big idea. This vector is perpendicular to this plane. That plane is given as parallel to the line. And so I, again, appeal to your geometry. That vector in must also be perpendicular to the line. A geometric appeal. Does everybody see it? Buy it? Okay. All right, so analogously for the other normal vector, and what that means is this direction vector that I'm looking for, conveniently, it's perpendicular to both of these given vectors that I know. I know these vectors because I read them straight off of the given equations. Everybody see that? I want a vector perpendicular to two vectors that I already know. And again, you gotta love the cross product. The cross product tells us how to do that. Boom. So now I have this V vector. And now altogether, notice I have, of course, we were given this point A. We just derived this vector V. And so I have a point on the line, I have a vector parallel to the line, and we have our old pre-existing construction for how to parameterize a line. There you go. And again, we win this little game. We've solved this little puzzle. Everybody with me? So notice, by the way, a couple of important things to notice about this. Notice how important the picture was. I'm a big believer in good pictures. It's just tremendously valuable. And by the way, this is not relevant just to this section. This is really applies to kind of the whole course. All of Math 219 is very geometric. And if you want to understand Math 219, then you need to understand and visualize geometry. And an invaluable tool for visualizing geometry is being able to draw geometry. If you have a picture, you have a huge advantage on understanding what it looks like, namely what the geometry is. So, does everybody buy that point? And again, pictures really, oh my God, you cannot undersell. There is no substitute for having a good picture. It's just nothing can do what a picture can do. So, if you don't have a picture, and that's the case we're in here, and by the way, usually, this question does not come with a picture. If you want a picture, you're going to have to draw it. So, if you're good at drawing in 3 dimensions, cool. That's nice. If you're not good, I think most students in this class, in general, come into this class where drawing 3-dimensionally is, that's hard. I don't really know how that. I'm no good at that. Right? It's a very common story. So, I just want to emphasize to everybody, this is something that you should take as part of how you're going to do well in this course, among many other things, of course. But learn how to draw 3-dimensionally. It's a really useful skill. This being just one of many examples. Now, to that end, y'all will recall that I have a YouTube channel. I'm not going to pull it up right now, but y'all know I have a YouTube channel, and that's where I put all the videos for the course, right? And I've got a bunch of other stuff on there. One of the other things that you might find really valuable, I have a playlist called Miscellaneous Topics. And in that playlist, I've put recordings that I've made special for my classes, intended for multivariable calculus specifically in almost all of the cases. And those recordings are on topics that I think Math 219 students could get possible benefit out of. So 2 of the recordings are about drawing and how to draw three-dimensionally. What's the difference between a good drawing and a bad drawing, and how do I develop this skill? What should I be thinking about as I draw, right? It turns out there's a few neat little tricks. And if you learn the neat little tricks, if you sort of digest and understand and practice how to implement a couple of neat little tricks, your drawings will improve dramatically. So if you feel like this is an area where you could use a little help, I strongly endorse looking at those recordings. They add up to about an hour. There's a lot to say. But there's some detailed discussion of the tricks, and then further detailed discussions, examples of how I use those tricks to draw some pretty complicated three-dimensional drawings. Okay, hope that's useful. Okay, so now we've in both of the previous examples, we've used what I'm going to call kind of a transitivity argument. Like on this argument up here, the argument I made was, well, the normal vector is perpendicular to the plane, and the plane is parallel to the line, and so these are parallel, and these are excuse me, I got it backwards. Again, misspoke, sorry. These are perpendicular, and these are parallel, and kind of because of that, these have to be perpendicular. Right, so it's sort of a transitivity being argued here. And then likewise up here, the plane and the normal vector are perpendicular. The normal vector and the y-axis are perpendicular. And then because of that, we conclude that the plane and the y-axis are parallel. Right, so again, kind of a transitivity. So the transitivities are very convenient geometric arguments to make. They're also, however, dangerous, because not all transitivity arguments that kind of at a glance look like they ought to be true, not all of them work. They're just flat not true. Right. So, for example, and this is just by way of a warning. Right. Look at this picture over here. That picture right there, certainly that vector and the plane are parallel, sure. And also the plane and this other vector also parallel, okay, sure, fine. Does it follow that this vector and this vector does it follow that they're parallel? Certainly not. Do they need to be perpendicular? Nope. There's just no relationship that you can conclude here at all, right? So now again, it's tempting to say, well, this is parallel to that, and that's parallel to the other. You're going to have this urge to, therefore, V and W are parallel. Again, just not true. Everybody see it? So you always have to think it through. And again, having a picture, invaluable, right? But make sure to think it through. And don't just write stuff down because it looks good. That'd be a catastrophic mistake. Here's another example. Let's see here. P and Q are perpendicular. Q and R are perpendicular. Does that mean that we have some relationship between P and R? Nope, not at all. Not necessarily perpendicular, not necessarily parallel, just no relationship, no conclusion. There's nothing here. Again, very dangerous. Okay. All right. So my rule on this, by the way, is if you make a transitivity argument, if it's a valid argument, cool, no explanation required. You have to say, and therefore these are parallel, or whatever. You do have to explain your reasoning, right? But you can just cite a transitivity if it's valid. But it better be valid, right? So do think it through. If you make a claim like this one, the argument's wrong. Okay. Alrighty. Okay, moving along. Let's see here. We've talked about parameterizing lines. I've talked about parameterizations as being point generators, right? Now we're going to sort of adapt that idea of a point generator to a two-dimensional thing. Previously, we've talked about parametric lines, parametric curves in 2 dimensions and 3 dimensions, but we have not talked about a parametric surface before. Right? So the general discussion of parametric surfaces is going to wait for a little while. We're not going to get to that for a while. But I do want to, while we're here, talk about parameterizing a plane. Turns out parameterizing a plane is no big deal. It's sufficiently no big deal, in fact, that you've already seen this as part of an old homework exercise from, I think it was 1.6, I want to say. And so you could view this as being a sort of a, here's, by the way, with the answer you should have gotten on that question, which I guess y'all are turning in tonight. So you can use this discussion for that if you like. Anyway. So the idea is, if you were given a point on the plane, and if you were given a couple of vectors, V and W, that are parallel to the plane, I claim we can use this information to parameterize the plane. In other words, we can use that information to generate all of these points X that are on the plane. And the idea is that, okay, well, if I start at my given point in the plane, right, then I can move, let's see here, you know what? I've made a bad color choice. I'm gonna make a different choice here. I'm gonna use red to describe the point I'm trying to generate. There we go. Okay, so I can use this given first vector to help me move by some amount in that direction. And of course, if I start in the plane and if I move parallel to the plane, however far I go parallel to the plane, in plus parallel, still in. Right? All right. And then, of course, I've got W still parallel to the plane, and so I can multiply. Multiply it by some scalar, move by some amount in that direction. Still parallel, and so again, in the plane plus parallel to the plane keeps me still in the plane. And the argument I'm going to make here is that this allows me, these two terms here in some sense allow me to move however far I need to in one direction, also however far I need to move in the other direction. And so you can get anywhere you need to get. And if I need to get to this point over here in the plane, fine. Some appropriate multiple of V plus some appropriate multiple of W added to the original point A, and you're there. So this is a parameterization. Now, we do get, as a result of this, we get 2 parameters, you'll notice. So let's see how color choices. 2 parameters. The parameters are S and T. And for whatever values of S and T you pick any S, any T, that generates a point X. Different S's and T's, you get different X's. And then we'll trace out the whole plane. What do you think? Everybody's happy with that? Cool. All right. So very similar to that homework exercise. Now, of course, the difference is in the homework exercise, they asked you to describe the points on just a parallelogram. Now, a parallelogram is part of a plane, and so that exercise, part of your answer is going to be to write this down, yes. But the additional thing that you have to think through is, how do I cut this down to describe just the parallelogram that was given? And short version of the answer, and of course you're welcome to come to office hours if you want further details, but what you're going to have to do is put restrictions on what the values of S are that you want, and what are the values of T that you want. And if you restrict the values of S and T appropriately, then you can turn this general plane parameterization into just a parallelogram. Alrighty. Okay. So quick example, how we parameterize a plane that contains 3 given points. We've already talked about how to find the equation. It's even easier to parameterize because, all right, to parameterize, all I need is, well, I need a point. Let's see, where am I going to find a point in this plane? Oh, cool, I've got 3 of them, so pick one, and I like the easy one. It's, why not pick the easy one instead of the hard one? It doesn't matter. And then all I need is 2 vectors parallel to the plane. We can use this same subtraction trick to get the 2 vectors parallel to the plane, and then we plug into the above form, and the parameterization is, well, it's exactly this, stolen from the previous discussion, based on the given point and the 2 now known parallel vectors. Everybody okay with that? Okay, so even easier than the equation in that case. Okay, this is a good stopping point, and we're out of time, so I'm going to draw the line there, and we will pick up here on Monday. Y'all have a great weekend. Don't forget, homework due tonight, 11 p.m. You're going to upload it to GradeScope. Y'all have a great weekend.